Welcome back to the second installment of the AP ECE Chemistry Chapter 8 Thermochemistry Problem Set Review. Let's take a look at question number 19. I'm Mr. Wilkosz. Question 19, you're burning a gram of salicylic acid and the temperature increases from 23.11 degrees Celsius to 28.91 degrees Celsius. The temperature of the bomb calorimeter increases by 2.48 degrees Celsius in a separate experiment when the calorimeter absorbs 9.37 kilojoules of energy. So the question is, how much heat is given off when 1 mole of salicylic acid is burned? The first thing you need to do is deal with the second sentence here. The temperature of the bomb calorimeter increases 2.48 degrees Celsius when the calorimeter absorbs 9.37 kilojoules of energy. Use that to number 1. Here I'm dividing this problem into 3 subproblems. Number 1, find capital C cal, the heat capacity of the bomb calorimeter. So rearrange Q equals capital C delta T, and you can find that the heat capacity of the bomb calorimeter is 3.79 kilojoules per degree Celsius. Next, you can use the idea that the heat energy that's absorbed by the calorimeter is the negative of the heat energy that's released from the reaction. So you can find that from the very first sentence that when 1 gram of this substance was burned, you released a certain amount of energy that increased the temperature from 23.11 to 28.91, and then you use your capital C cal from part 1 we just did above, and you can find the amount of heat energy that's released when 1 gram of this substance burns is 22 kilojoules. Thus, the heat of the reaction is negative 22 kilojoules because we actually increased the energy in the calorimeter. And then the third part, you know, if 1 gram releases a certain amount of energy, can we figure out how much 1 mole releases? And the answer is yes. So you convert the grams into moles and you find out how many moles you actually dealt with. And then you should see that this is a negative 22 kilojoules per 0.00725 moles of this stuff. So for 1 mole of this reaction, it should be negative 3,040 kilojoules, and that's per mole. So that should read per mole. Alright, let's take a look at problem 23. Problem 23, you're dealing with a reaction of nitric acid with hydrogen gas to make ammonia and water, and this particular reaction releases 637 kilojoules when this reaction goes. So they want the enthalpy change. Now we're dealing with state property, not just heat. They want the enthalpy change when 1 mole of hydrogen gas reacts. Well, if you look at the equation, 4 moles react there, so you need to take that enthalpy change divided by 4, and that's how much energy would be released when only 1 mole of hydrogen reacts. So they want to know what the enthalpy change, delta H, is when 10 grams of ammonia react with excess steam to create, the nitric acid, the gaseous hydrogen nitrate and the hydrogen gas. A real important thing is that this is actually the reverse of the previous equation. So that means your delta H is negative. So I rewrote the equation now backwards, and I'm highlighting for you, like, look, it's positive 637 kilojoules because this is the reverse of the previous equation. But then this is just like problem 13, section C, where you're taking a given mass, converting it into moles, and then using your thermochemical information as another conversion factor stoichiometrically. And the final answer is 374 kilojoules. Let's take a look at problem number 31. In problem 31, you're asked to consider how much heat is needed to take 10 grams of liquid bromine at a certain temperature, that's 22.5 degrees Celsius, to vapor at 59. And they ask you to look at some tables and find some information. So there's 3 parts that are here. You're finding the enthalpy change to take the liquid bromine at 22.5 degrees Celsius to the boiling point, which you get from the table, as 59 degrees Celsius. Then you're finding the energy required, the enthalpy change required to get the liquid bromine at 59 degrees Celsius to gaseous bromine at 59 degrees Celsius. It's a phase change. It's going to cost some energy to do this. And then the final thing is a Hess's law thing. If you know what the energy change for the first 2 parts are, you can figure out what the energy change is for the third part. So here's your constants out of the table. And here's the mathematical work to do this. For part A, the enthalpy change is mass times the specific heat of bromine times the temperature change. For part B, we're just dealing with a phase change, so it's moles times delta H vap. For part C, you sum them all up.